you know, you can take the shaking the foundation by really taking the foundation at several levels, philosophical level, doing hardcore quantum gravity. I always try to fight from the side this kind of problem. So,
hello. So, welcome to the new episode of the Dialogues on the Foundations. It's a series of meetings with physicists and philosophers in the context of a program of the Center for Advanced Studies, a research focused on new foundations for physics, which I am coordinating. So my name is Daniele Oriti. I'm a theoretical physicist working on quantum gravity at LMU Munich. And today with me, my partner in crime is Stefano Liberati, Professor Stefano Liberati, from SISSA Trieste. And welcome, Stefano.
thank you for inviting. Ciao.
So let's start. So you worked on many things. So it's a bit difficult to choose exactly where to start from. So let me just say, you are an expert in black hole physics, classical, semi-classical, and let's say quantum. You are an expert in quantum gravity phenomenology. What else? You worked on spacetime thermodynamics and in analog gravity models in condensed matter. And through that, I would say that you're also an expert in emergent gravity scenarios. Now, we'll try to touch a bit of all of that. But before we do you feel you're shaking the foundations?
I don't know if we will.
Hey,
Well, let me put it this way. I think that I'm trying to look at the foundation of things by taking some kind of non-direct routes. You can take the shaking the foundation by really taking the foundation at several levels, philosophical level, doing hardcore quantum gravity. I always try to fight from the side this kind of problem. So, in particular, the kind of things I've been working the most, the quantum gravity phenomenology and analog gravity, can be considered as a kind of side routes that might lead to important lesson, I hope, for what, for example, quantum gravity should be and how we could see the effects of quantum gravity.
So you're supposed that people who work on quantum gravity head-on are particularly brave or particularly...
You may consider them some sort of kamikaze, but yes, I mean, particularly brave. I mean, not necessarily suicidal, but it's a very tough problem, and it's a problem which is very difficult to advance. So yes, I consider them particularly brave. That for sure. Kamikaze maybe sometimes.
So brave is a diplomatic way to put some other concept. And I'll leave it as it is. I don't want to investigate further. So let's start with some of these side directions. So you worked on black holes. Now, people have heard about black holes. They know we observe them in the sky. Not with naked eye, but we do observe them, that we do a lot of physics about them. What's puzzling about them? Isn't everything under control?
Well, there are several things that one may say about black holes. First of all, they are the simplest objects and still are the most difficult to understand. They are the simplest because they are just purely gravitational objects. Nonetheless, they present several challenges. They present several challenges already at the level of classical gravity, about the theory of Einstein gravity, because if you basically use Einstein gravity, you are led to the conclusion that unavoidably there must be a singularity inside a black hole. So basically, space-time as we know it ceases to exist inside a black hole. And this is a challenge for any physicist because it's basically telling you that you don't have a theory which predicts what is happening inside a black hole. And you may say, okay, who cares? It's inside a black hole, we cannot see it.
I was about to say that's fine.
What? Sorry?
I was about to say that. Well, it's not there.
It's not so obvious because you see the standard law is that there you need quantum gravity, and then quantum gravity will take care of it. But what you're going to see outside is going to be undistinguishable from the black hole that is a solution of the equation of general relativity, that means of the Einsteinian classical theory. But the thing is not so obvious. I mean, if you try to see how space-time can be regularized by quantum gravity, even without knowing quantum gravity, there is a general taxonomy that you can put down of how you can avoid the singularity. And the lessons that you draw is that it's very difficult to avoid the singularity and to confine the effect of this avoidance inside the event horizon of the black hole. You do have subtle differences outside. Now, they may be difficult to see with current observation. Nonetheless, the objects that have a regularized core in general have different properties from general relativistic black hole. And even that we expect that somehow quantum gravity do the job. I mean, somehow the core must be regularized. Mm-hmm. Then it's worth checking for which kind of different phenomenology you have.
Okay, so you would say that the difficulty in curing the singularity is not so much to curing it itself, but to make everything regular and well-defined without destroying the picture that is under control from classical relativity at larger distances or even outside the black hole.
Yes, you have two kind of issues basically that are emerging from the investigation that are currently going on. One is stability. You generically produce structure which are unstable inside the black hole. Mm-hmm. So the black hole needs to evolve. It cannot be. So you have an issue because you know that whatever is the object that we call black hole in the sky, it looks like it's stable for a long period of time. So generically, instead the stability you may find when you regularize the core, they tend to be rapid, fast. So you need to have, in a sense, a dynamical situation that becomes stable on long times, and though not completely stable. Mm-hmm. This is a complication theoretically that offers an opportunity for phenomenology, in the sense that if you have something that is not exactly the general relativistic black hole and needs to evolve, then you have a windows of opportunity to check this new physics. And the reasoning that is leading to this new physics is very general, doesn't rely on the detail of the quantum gravity theory that has to come in order to regularize the singularity. And the other issue is that even if they are stable, if you stabilize the structure tend to have signatures of the fact that there is the stable core beyond the event horizon. That is very interesting because it offers a tiny but present windows of opportunity again to see the fact that the object that you have in the sky has basically gone through a phase in which quantum gravity has done the job to stabilize the core and remove, this singularity displays where space-time ceases to exist.
So you're saying that, if I understand correctly, not only we shouldn't rely on the fact that the singularity is hidden behind, inside the horizon, hidden forever from our eyes, but in fact we should take advantage of the fact that whatever cures the singularity can be seen outside outside the black hole, and that can lead to observable effects. Is it also gravitational waves that can notice that?
Well, in general, you have that the structure of the black hole can be modified depending on the way you regularize the singularity to scale which are comparable to those that are mining, for example, the way after the formation of the black hole settled down. Mm-hmm. And these are signatures that we see in the gravitational wave signal. So there is a small chance that you can also see this. Of course, you need basically observation which are more precise than the one that we're able to do now. You need what is called jargon, a signal to noise ratio. It means basically you need a signal which is very clear, very neat, clean in such a way to see these tiny deviations. Still, they are there. In principle, you have a target for your experiments. If you have a picture where, how big this modification. We are not yet at the prediction of how large they should be. So we are not yet at the level in which we can tell the experiment, look, this is what you should expect. But what I find interesting is that, without relying on the detail of the quantum gravity theory, if you assume that inside the core of the black hole is still, after maybe a transient phase in which you need quantum gravity, settle down to something where you have a well-defined space-time everywhere, then basically there aren't many solutions to the problem. There are basically only two ways to regularize, to smooth out the singularities. And these two ways have different properties. And they can lead also in the region, they could also be unstable in a way in which the object that you end up forming maybe doesn't have an horizon, but is an ultra-compact object without an horizon. So that would give another kind of phenomenology that we can distinguish from the one with the horizon.
Oh, but wait. But then I thought I knew one thing about black holes, which is that they are black. And,
yes.
And now you're saying that they may not be black, because if there's no real horizon, then in principle things can come out.
It would be nice for phenomenology, but the answer is no. If you take an object and you make it more and more compact, of course, the big issue is that how this object will basically be self-supporting. So you need some new exotic physics that we can discuss in a separate. But imagine you have this exotic physics supporting this object. And the idea is that this object is not formed in the collapse. You form a trapped region. You have an unstable regular black hole that could end up with something without horizon. Then, in that case, this object would be ultra-compact, very close to form an horizon. Then the huge redshift that you have at the surface basically makes the object not totally black, but very dark gray. So what is happening is that if you do, for example, try to cast constraint on the compactness of this object by looking at the reflection of radiation that is impinging on the surface, you find that due to the extreme bending of light close to this object, which is very close to the would-be horizon, basically very few radiation escape, and if the object moreover has some kind of opacity, basically it's very difficult to see the difference between an ultra-compact object of this sort and a black hole.
Okay, so black hole versus ultra-compact is like black versus basically black.
Dark gray, ultra dark gray. I don't promise that. But from ultra-compact, basically you would have, for example, the shadow of the black hole that has been on the newspaper, so the picture that we took of the supermassive black hole M87 or the black hole at the center of the galaxy, Sagittarius A star. They would look basically the same. It would be very difficult to discriminate between these ultra, because basically the shadow is very sensitive to a region which is outside of the horizon. It's basically a region where there are some circular orbits for lights which are unstable, and that would give you would determine the main features of this image.
Okay. So but these are more speculative situations that we can leave to the very brave people.
Yeah, these are more speculative, definitely, because in a sense, this could be only seen as a possible outcome of the stability I was talking about. And even these compact objects have their own instabilities. They tend to be unstable for other reasons, different from the one of the regular black hole. And this is also very interesting, you see, because it may come up that somehow you cannot have a stable object mimicking a black hole of general relativity because of this instability. And then the lesson you may draw is that maybe you cannot escape the formation of the singularity, in the sense that you will have permanently a region inside a black hole where you need quantum gravity to describe what's going on. There isn't any transient. There is really a region where space-time does not exist. And if you think that space-time is somehow emergent from something more fundamental, like a fluid from some molecular system, then there you need the description at the molecular level. You cannot use the thermodynamics to describe.
This is fantastic for me, given that I work on that. But before we go on this, this type of scenarios, suppose we forget about all the more speculative cases. No, we have a black hole described by GR, and then we have standard, fields, particles, and moving around. In that case, they are black.
Yep, but it depends at the classical level or the quantum level.
Let's say semi-classical.
Yeah, what happens is that, as we know, they evaporate. Now, the produced particle. And,
I may have heard about that. So
yeah, what is happening is, well, the heuristic picture is relatively simple. We all have experienced that the gravity, basically, for example, the gravity of the moon on the Earth creates tides, right? Tidal forces. That is where really gravity lies, in this fact that you tend to strip apart points when you are subject to the gravitational field of the object. In the case of a black hole, you have to think that basically the gravitational field, especially for a black hole which is very small, the gravitational field close to the horizon is going to be very strong. Why? Because the smaller the black hole is, this closer to the singularity, where in theory the curvature of space-time is ripped apart, so it's both, is huge, the horizon is. So you have two things. You have that in quantum mechanics, basically, virtual particles are continuously created and destroyed within basically the allowance of the uncertainty principle. But at the same time, you are close to the event horizon of a black hole, then you can always have that while these virtual pairs detach, are created from vacuum, they would like to reconnect and disappear again, but the tidal forces close to the horizon of a black hole basically breaks them apart and give the energy to make them basically a real particle, not just the one that are existing in this ultra short.
So there is this beautiful pair of objects that would like to connect, and instead one of them is kidnapped by the black hole.
Well, the tidal forces, if you will be falling into a black hole, and basically what will happen to a person? A person will be spaghettified because the attraction at his feet will be different from what he is feeling at his head. And this difference, basically in gravitational force, will strip the person, basically elongate it and spaghettify it. And it is a quite interesting way of dying. Not that I would like to experience it. I think it's like a kind of medieval torture. But anyway, if the black hole only were very, very large, I mean, for very large black hole, for supermassive black hole, you can fall into the ground without being spaghettified. And this is because the horizon that is very far away from the region of strong gravity at the center where the...
So you're saying there are these two particles, one is falling inside and cannot reconnect with the other, and the other escapes. So there is
exactly that is falling inside. Yeah, but you have basically to conserve energy because the energy of the vacuum is zero. So if the one that escapes from outside has an energy which is positive when it reaches you very far away from the black hole, the other that is falling inside must have a negative energy. So when it adds up to the mass of the black hole, it decreases it. So the black hole has a lower mass. The mass is also setting the size of the horizon. So the horizon shrinks. The black hole then has stronger gravitational forces close to the horizon and creates more particles. And then this is a kind of parasitic process. So this is basically in the nutshell what is Hawking radiation. Hawking radiation is basically the strip apart of these pairs, and it is the fact that one escapes to infinity, the other one has negative energy with respect to infinity and decrease the mass of the black hole, and the black hole becomes smaller. By this,
bye.
Well, the black hole it tends to evaporate, and it becomes hotter and hotter, and it becomes smaller and smaller, basically, because this process is more and more efficient the smaller the black hole is. And the particular thing is that, this radiation that is reaching infinity has a thermal distribution. It's like a black body radiation. So it has a fixed temperature, and this temperature basically goes like the inverse of the mass. So the smaller the black hole becomes, the closer is the horizon to the singularity, the hotter it becomes. So the interesting point is that this was the first window of opportunity to connect general relativity and quantum mechanics, because this is a quantum mechanical process. But there are several intriguing things about it. For example, there are laws of thermodynamics of black hole, which are the analogy in a complete analogy with a law.
No. Wait a second. So that we have a region of space, which is the black hole. Okay, it's basically black, very dark gray. Now you're telling me that it evaporates, and that it has it's a thermodynamic object. So there is a temperature and all the other thermodynamic quantities associated to it.
Yeah, and it's it's really puzzling if you think about it, because exactly if you take general relativity, and a black hole normally is considered to be sitting in a vacuum. No, there are no particles around. Of course, it's an abstraction. Astrophysics, they don't sit in vacuum. But let's take that it's sitting in a vacuum. It should be completely stable and completely black. Nonetheless, it was found in the 70s that this black hole were satisfying laws. They have basically laws of general relativity, which were in close analogy with the law of thermodynamics, standard thermodynamics. And what didn't make sense is that an object to have this thermodynamical law needs to have a temperature. But the temperature was only found a posteriori by Hawking by using quantum mechanics, or more appropriate, quantum field theory. That means the theory of quantized fields for describing matter on the black hole spacetime. And then only then it came up the process that I was talking about, because this process that I was talking about is relying on the first point that you have these beautiful pairs that you don't have at all if you are in classical physics, if you don't include quantum mechanics. So it's very strange if you think of it. General relativity somehow knew that the temperature need to have a temperature, but this temperature comes up only when you use quantum mechanics. How did the general relativity knew about quantum mechanics in the first place?
Mm-hmm. But there are two things that I find extremely puzzling about this story of black holes as thermodynamic objects. We'll touch the second in a while. But first of all, I mean, we said that the black hole has an entropy, it has a temperature, and you can attribute the other quantities like energy, heat, and so on to all the matter around it. And that they satisfy laws that are just like the ones of standard thermodynamic. But okay, the black hole evaporates and loses energy, as you explained, and then it becomes smaller. And this process keeps going. And at some point, it should either disappear or what?
Well, as this is trying to happen, it becomes hotter and hotter, and then you need again quantum gravity to see the end. So you need people like you that comes and that
the kamikaze.
The kamikaze, and then you need to have an exploration of what is going on at the very end of the black hole. But somehow the impression, I think that what we are learning is that somehow something deep is happening all the way through the life of the black hole, because you see, basically the problem of describing the last moment of the evaporation, where the black hole is so small and so hot that you need basically to quantize gravity to describe what's going on, it is a well-known problem and very hard one. But somehow there is another problem that is there, which is the problem of information loss. You know that somehow if this process goes on too long, you remain with a black hole which is too small and not enough energy inside to re-emit the information that was stolen from the outside universe by the inflow of matter into the black hole. You see, the problem is that information costs energy. It's not that this comes for free. To transmit information, you need energy. So the problem is that as the matter falls into the black hole, basically you have that there is all this information that is stored inside the black hole. And if the black hole would sit there forever, there would be no problem, because in a sense it would not be accessible, but it will be in this kind of vault but it's there, right?
You had the books in the bookshelves that I haven't read.
Yes, okay, exactly. It's like a book.
They are there, and it's okay.
That you will never be able to read.
But
it's
nothing lost.
Exactly. But the problem is that instead the black hole evaporates. And at the end of the day, the problem is that it's emitting radiation, Hawking radiation, but this radiation is thermal. So it's, in a sense, the less informative form of matter you can emit. And from this point of view, is a puzzle because it looks like you have this loss of information. And of course, in quantum mechanics, instead, this is not what you would expect. In quantum mechanics, somehow this information has to be preserved. You should be able to write a formula where you have incoming matter, black hole, outcoming matter, and final space-time. And then this should be an evolution that in which basically the amount of information is redistributed but never lost.
Okay, but
instead,
it's that. Sorry, this means that either some of the basic principles of quantum mechanics or some of the basic principles of general relativity, so the two set of principles that we use to describe this evaporation process, have to go. So
yeah, apparently so. And the problem is that this has to happen well before the black hole is a Planck scale. Because if the black hole, Planck scale, is the scale where quantum gravity should be relevant. This has to happen well before that, because at that stage of the black hole evolution, there is not enough energy left to release in a final burst of the information. So you expect that some place at the middle of the lifetime of the black hole, there is the so-called page time, which is an estimate, is basically when the black hole is reduced to half of its entropy, which is proportional to its mass. Then at that point, basically, you should have started somehow releasing the information that you have stored. Otherwise, you don't have enough energy to do that. This is a problem because this can happen for macroscopic black hole, not for black hole where you would expect quantum gravity to be already, determinant in describing that.
So somehow this profound revision that quantum gravity has to bring cannot even be confined to the singularity. It has to be really affecting the whole description of black holes, including the evaporation, even for macroscopic ones, because it's just a matter of size that, smaller ones evaporate in a stronger form, but even very large black holes evaporate. So the process would be there for, very classical, apparently classical objects.
Yeah, with the caveat that the very large black hole in the universe do not evaporate because there is the cosmic microwave background, the liquid radiation, for example, from the Big Bang that is setting a kind of thermal bath. So you need to be hotter than that, and a large black hole, given that the temperature goes like the inverse of the mass, will be very cold. So
so you wouldn't notice.
You will need to wait a very long time for the universe to expand to the cosmic radiation temperature to go even below the 2.7 Kelvin that it has now to basically start to see this black hole.
It's okay. I mean, quantum gravity researchers are not only brave, also very patient.
Yeah, but it should be also be unbelieving, or you're counting on the future generation of quantum gravity research, probably.
Anyway, so let me touch the second aspect that I find somehow, tantalizing about all the story of black hole evaporating, having thermodynamic properties and so on. That, black holes at the end of the day are just peculiar regions of space. So you would think that if a black hole has thermodynamic properties, then space in general may have thermodynamic properties, and space-time in general may have thermodynamic properties. Would you agree? Do you think that is that something that people are working on?
Yeah. There are some ideas that, for example, goes under the name of space-time thermodynamics. There was a seminal paper in 1995, but Jacobson that was showing that basically you can use basic assumption. The fact that it's true that space-time is curved in general relativity and then describe basically gravity, but it's true that locally is basically flat. So the point is that around each point of space-time, you can construct basically a kind of I don't know how to say it without being too technical, but basically what you can consider is that around each point of space-time, on each point of space-time, you can consider like local analog of the black hole horizons, in the sense that they can always consider observers which are uniformly accelerated that will see things very similar to the horizon that determine the black hole thermodynamics. If you apply to this horizon the same laws of the thermodynamics, basically you ask that they react to flux of matter in the way you would expect, like you have learned, like in black hole, which is also like in thermodynamics. Then you can work backward and derive the equation of general relativity, the one that are determining the space-time. And this is quite amazing because it's like you can get the dynamics of the space-time, the general relativistic equation, from simple consideration concerning the fact that around each point of space-time, if you take into account, again, quantum mechanics, and the causal structure of space-time, the fact that at each point of space-time there is basically a notion of causality, which is determined by the light comes, basically the structure of causality that is determined by the speed of light. Then, just with this basic assumption, you can reconstruct the equation of general relativity, which is really telling you that this theory may be, in a certain sense, emergent, right?
So I mean, so let me see if I understood. So the point is that so a gravitational, to stand still close to a black hole, we have to sort of win the pull of the gravitational force, that will attract us towards the center of the black hole. So to some extent, we have to accelerate. So all the properties that we were discussing about black holes, at their horizon, can actually be simulated by thinking of what happens to somebody who is accelerating in standard flat space with no gravity and so on. And you're saying that the thermodynamic properties that we attribute to black holes, we can in fact also see them realized in a regional space with respect to people who are accelerating locally and so that space itself can be attributed in whatever small region can be attributed these thermodynamic relations, thermodynamic properties.
Yeah, the basic idea is that is one of the tenets of Einstein's equivalence principle. You can always trade gravity for acceleration, especially if you are in a gravitational field where, for example, the convergence, the tidal forces are not so strong, right? So if you are in an elevator, it's very difficult by very local experiments to discriminate if you are in an elevator accelerated upward and then you are pushed toward the bottom of the elevator, or you are in an elevator which is closed, is still in a gravitational field, for example, of a very large planet. Then if you do very local experiment, you don't see these tidal forces very clearly, and then basically you may be fooled to know, you don't know if you are accelerating upward or you are attracted downward by a massive body. The same things can happen in proximity of a black hole. To stand still close to the event horizon of a black hole, as you said, you need to have a constant acceleration. But then you can trade the same kind of observation should be made by someone in flat space, which is constantly accelerating. So as the first guy sees an horizon, also the second guy sees an horizon. As the first guy sees radiation, also the second guy will see some thermal bath at a constant temperature. That is called the Uru temperature. And then this analogy goes on that if you impose that also the second guy sees the same kind of thermodynamical laws that the first guy sees, the one closest to the black hole, then you can reconstruct the equation of general relativity. And that is quite amazing if you think about it.
Well, so indeed, so it's already amazing that to a regional space I can attribute an entropy, a temperature, and so on. But then it's even more amazing indeed that you can reconstruct the dynamics of general relativity or the gravitational field from these thermodynamic relations. This would suggest that space is somehow made of constituents that collectively we describe in terms of a gravitational field. So that you attribute to them to these constituents, these building blocks forming a regional space. You attribute an entropy and all these statistical thermodynamical properties, and then you can translate that into geometry, and it becomes the equations of general relativity.
Yes. And you see, while there is also a subtlety here that I like to stress, is that if you follow this path, you realize that there isn't just the equation of general relativity that you reconstruct, but in general, you will have also in your equation, thermodynamical equation, terms that are corresponding to what are normally in thermodynamics is called a match dict or internal entropy production. What this is that when you hit, you basically imagine a hammer on a anvil. The hammer on a anvil generates waves on the anvil. And basically the hammer and the waves are basically what normally you can consider the part of that goes in the general relativistic equation. But the hammer, when it beats the anvil, generates another things. Why? Because, you're not generating only these waves in the anvil. You're giving energy also to the internal degrees of freedom, to the internal
the molecule
component. What is the molecules that constitute the anvil. And then you don't see it, it's something that is in the structure. This is what normally goes under the name of a match dict or internal entropy production. And this part is there. And the fact that it's there also in this derivation a la Jacobson is telling you that is strongly suggesting that there are internal degrees of freedom. There is a way of saying, if you can heat it up, it must have internal degrees of freedom. So it looks like there are terms that are corresponding to heating it up the space-time. And these terms are normally what are also related to the loss of energy to do gravitational radiation.
Mm-hmm.
And this is quite interesting, because it's telling you it gives you another perspective. Gravitational radiation, gravitational wave, we normally think of them as a deformation, as waves over a lake, right? But if they would be waves over a lake, we would be able to describe them as usual, as in essence, in a very traditional way, and attribute to them a conserved energy in the standard sense of general relativity. While these other pictures seems to suggest that it's just an approximation to consider them wave. What they really are excitation of the internal degrees of freedom of space-time. And in a certain sense, it looks like light in one direction is taking longer to propagate than the other direction. But because light has to propagate on this fundamental lattice that at the fundamental level is space-time. I mean, you have to believe, of course, that there is an intrinsic discreteness and quantumness of space-time.
No problem with that.
But most of the
emerging, just like a fluid emerges from the atoms or the molecules, is something that was puzzling at first, but also so inspiring that we are trying to realize it in a very concrete manner. I mean, in our group here, I mean, it's an idea that I hold very dear. So I thought it was totally crazy, but now you tell me that there are a number of reasons to find it crazy, but also reasonable in a sort of paradoxical manner.
Yeah, the complication is that you have basically to diverge space-time, so your fundamental theory cannot live in space-time, and we are not used to even think about this kind of I mean, of course, people in quantum gravity has to learn how to think about it.
Yeah,
but most of the physicists, I think, are basically have this imprint that everything happens in space-time. And so to emerge in space-time, you cannot be circular, you cannot emerge. Of course, there are models where you have a kind of container space-time which has without gravity, which is basically flat. And then you have ways to emerge a system which has, has the property of curved space-time and that's the laws of general relativity. But in a sense, this fictitious flat space-time, you call it space-time just because you're used to it, but in principle is just a mathematical construction.
In fact, I can confirm that the hardest part of working with all these models, beside the mathematics, is indeed to have any intuition of these fundamental degrees of freedom, these atoms of space that we want to describe. Then, of course, this difficulty translates in a number of mathematical challenges, because all our models, all our, well understood theoretical frameworks assume that there is a space-time in which we have atoms and particles and so on. And as you said, I mean, now we are talking about the atoms of space, somehow the constituents of space itself. And so their description cannot be based on some pre-existing space or space-time. And that's indeed the biggest challenge. But this brings me to another point of another area that you explored in your work, because we were discussing, molecules, atoms forming fluids, and that this is a good analogy for space-time being formed by some more abstract atomic constituents. So what is this analog gravity business that you worked on and that people work on? I mean, what's the idea there?
If you like, it's taking too seriously this idea, you may say, or if you like, it's an inspiration for this idea of emergent space-time. Analog gravity is a very simple concept at the core. I mean, in many systems of natures, you may have that the concept of a space-time and of matter moving on a curved space-time is meaningfully realized. So let me try to be concrete. If you take a fluid, and a fluid in what we call a superfluid, something that is not affected by relevant viscosities, and has a laminar flow, basically very simple flow. Now you ask yourself, okay, on this flow, what is the equation describing the propagation of perturbation of little wave on the flow? Well, you can do this analysis in a very standard way. You have the equation of heterodynamics. You have continuity in other equation. You linearize your background field. The velocity of the flow. You consider perturbation for the density, for the velocity, and then what you find is that this flow, the perturbation over the flow, propagates like normally we describe matter field propagating on a curved space-time. And the curvature of the flow of this emergent space-time is determined basically by the property of the flow, the background density, the background velocity, and so on. And you realize something, that you can simulate a rich variety of metrics, not all the metrics that GR can produce, the general relativity can produce, but many of them, but the most interesting one, let's say. And for example, you can generate a region where your flow goes inside a kind of hole, a drain. And basically what is happening is very simple to see that you can simulate what is the analog of a black hole. Imagine that your flow becomes supersonic at some point. Then if you have sound waves, on the flow, which are the perturbation we were talking about.
Like you're falling inside and you shout for help.
Yeah, you will basically imagine you send one of your students with some.
Oh, wait, I note down the idea.
Yeah. So you can send him and he say shout, and you will sound, from in the water, you will see. And at some point, once your student passes the region where the flow is becoming from subsonic, supersonic, then of course the sound wave, even if they go outward, they will be dragged down, a bit like a salmon that is going against the stream of the river. If it is not swimming sufficiently fast, it will be dragged down, even if it tries to go upstream. So that is the analog of a black hole, and the analogy is that the mathematical equation is the same. It's the same up to some approximation. What is the approximation? The approximation is that this space-time, this analog space-time, is not continuous at all scale. It's not something that is relevant for long wavelengths. No. Now, what happens? That in general, the the waves propagating on the space-time will have a modification. When they become too short scale, they will see that there is discreteness suddenly. They will start to propagate in a different way. And this different way is basically another interesting aspect, because there is a whole stream of research which this discreteness one of the effects is that it may breaks basically special relativity locally. Okay, and then limit of the speed of light.
So it means that so you told me that you can simulate a black hole in the lab.
Yes, actually we did. We observed a black hole, the analog of black hole, and we even observed the analog of Hawking radiation in a lab. Nowadays, it is something that was reproduced, because it makes certain sense. You have the same equation. When you can quantize the field, you can use quantum mechanics on this effective field of propagating on this emergent space-time. The result should be the same equation, and what you get is exactly that you predicted that within a range of applicability. It's not a perfect analog, but within some wavelength, you expect to find the Hawking radiation, and you observe Hawking radiation.
Okay, so wait a second. So you can simulate a black hole, you can simulate the Hawking radiation. I've heard that you can also simulate cosmological, scenarios in which the universe expands and so on, and you have particles moving on an expanding universe. And but you said that this is only true within some approximate regime. Now, you also said, however, that when you go beyond this approximation, you find a distinctive behavior of the fluid system, which is different from what general relativity would predict. On the other hand, there are at least ideas that also general relativity has to be improved or modified with effects which could be similar to those that in fact are known to be there in the fluid, like modified dispersion relations, or this type of fundamental discreteness. So a priori the analogy could extend even beyond this regime of approximation, at least in principle. But where is it that it fails? You're not going to tell me that you can actually have a black hole in the lab. When can you tell the difference?
The very interesting point to me is that you may ask yourself, is Hawking... Okay, first, let me say one thing. In analog gravity, you simulate a field propagating on a curved space-time. The equation describing the dynamics of the space-time are not the equation of general relativity, are the equation of hydrodynamics. They are not the same. However, Hawking radiation is something that is produced only by looking at the dynamics of a field of a curved space-time which has a black hole. You don't need Einstein general relativity to reproduce Hawking radiation. This is why we can simulate in a lab Hawking radiation without simulating general relativity. Now, say that there is the issue of deviations. In analog gravity, you have the microphysics. When your waves become very short wavelength, it is important that you realize that this is an emergent space-time, and you realize it in the fact that basically the propagation of your waves is not bounded anymore by the speed of sound, which here is the analog of the speed of light, but can in principle be faster. This is a breakdown basically of the fact that you reproduce special relativity locally. That means that the speed of light is the upper limit locally. Now, the point is, you may ask yourself, is Hawking radiation robust against this, ultra short scale deviation from the standard scenario? And surprisingly enough, or depends, maybe not so surprising, the answer is yes, it is robust. And it's robust when the typical scale that determines the temperature of your black hole, the analog of the mass in the case of the analog, which is the analog of what is called the surface gravity, the acceleration that you need to stand still close to the event horizon of the black hole, is very different in energy scales from the scale at which the new physics, the discreteness can be felt. So basically, if your black hole produces on average particles which have a wavelength which is very long with respect to the discreteness.
Which is
scale.
the average distance between the atoms.
The separation of scale protects Hawking radiation.
Okay.
And that is why we can see we have a regime of validity in which you can reproduce basically Hawking radiation in the lab with these acoustic black holes.
Okay, but the point is that the analogy breaks the moment you have to call into action the equations of the background, the equations of space-time itself.
Exactly. For example, you may ask yourself how this analog black hole evaporates, because when we say that normally black hole evaporates, what we have taken into account, the back reaction of the flux of Hawking radiation that is lost, and then we were saying the negative energy partner that are accreting into the black hole, and say then you need to describe the evaporation, the dynamics induced on the geometry. You need the Einstein field equation. Now, it's interesting enough, in some cases, even in analog gravity, you can see that the black hole shrinks. But still, the calculation relies on different equation. You can imagine why physically this has to be so, because if you're emitting Hawking radiation, someone, there is no free will in physics. Someone has to pay the energetic bill. So in the case of the analog black hole, if you don't basically insert energy from outside, it's the kinetic energy of the flow that has to pay the bill for the created particle. If the kinetic energy of the flow decreases and you have a sink, then basically the point in which you reach the sonic flow, a sonic velocity, it is going to be closer and closer, deeper and deeper in the sink. You have to go down deeper to arrive to the same sonic point.
This is the idea of the black hole shrinking.
Shrinking, exactly. So again, it's just a byproduct of energy conservation that somehow you have to...
So again, let me understand. So you can see, despite the difference in the dynamics of your analog black hole from an actual black hole, because in one case you have the aerodynamic equations, in the other you have the equations of general relativity, at least the qualitative aspect that the evaporation takes away energy and so the black hole shrinks and so on, this is also reproduced. Is the details of how the black hole evolves that will be different in the two cases because the underlying dynamics is different.
Yeah, exactly. But there is even more time, and another tantalizing feature that even yet is like a striking one. So let's imagine that you want to play this game until the end. So let's take a system of relativistic atoms, and let's consider basically that they do some sort of condensation so that you have a superfluid limit, and you do play the game we just said. Now you have this perturbation that are propagating on a curved space-time. Okay. Now you say, okay, you can always adjust this system. You can show that you can adjust the system in such a way that this perturbation, then you consider this metric, and then you ask yourself, okay, take the equation for the acoustic geometry, the one felt by this perturbation, and I want to describe the equation governing the fluid as equation governing this analog geometry. You can always cast this background equation in a form which is extremely close to Einstein general relativity. Actually, given that here you have all this basically a very simple scalar degrees of freedom, that means a field that has only property to give you the value of a function at a given point. Then what is happening is that you get a primitive form of general relativity. The theory of gravity that was basically a progenitor of general relativity, which is Northstone gravity, a theory that was developed in 1913 as a relativistic generalization of Newtonian gravity. And you get the same equation emerging from the system. So you don't get general relativity, but if you want to express the equation for the governing the background flow in terms of the emergent metric, then you get a form which is down close to general relativity. It tells you that there could be some lessons here. Of course, the condensed matter system we work with are too simple. The universe is not, a condensate of atoms. It must be much more complicated than that. but still, it was not obvious that you can get this equation so close to the one of.
So you're saying that there is at least hope that even the dynamics of the background could, in principle, be simulated in the analog system, in the condensed matter system. In fact, I mean, we have ideas to do that through a different route than the one you mentioned, and it's something I'm quite excited about. But I will tell you in private, not in public. Well, it's still half baked, so I mean, I will tell you what the idea is, but I have no big claim to make. But before we go there, what do you think is the longer term goal of all of that? And suppose that we manage to reproduce, at least at the level of the equations, also the dynamics of general relativity. Not just the behavior of fields and particles on a solution on a given background solution of general relativity. Is it still an analog system, or you would have literally the physics of general relativity and quantum gravity there? I mean, it sounds like a stupid question, and you're used to my stupid questions. But my point is simple. I'm just saying that. I'm trying to make a deeper point for once.
After sophisticated many glasses of wine.
No, trust me for a second. I'm trying to say something meaningful. Suppose that we have an exact match of the equations. Now, it's not the case. Fine. So far, it's not the case. But suppose that works. By some clever strategy, we managed to have the full set of equations of hydrodynamics and quasi-particles in a fluid and waves and so on, exactly translated in and from the equations of general relativity and fields in general relativity, including the background dynamics. Then what will be missing? Why would that be the case that the physics will still be different? It's a question about how much we can or we should rely on just the mathematical analogy, because this is a question that people ask for analog gravity systems. Now, they say, yeah, okay, you are reproducing something that looks like Hawking radiation. Yes, it satisfies the same type of equations, but that is still not a black hole. So how do you know that you're actually capturing the physics of a real-world astrophysical black hole? And normally one would say, yeah, okay, you're right, because we are not capturing for sure all the dynamics of the background. But suppose that is captured, where will you draw the limit? The difference between
if it is a condensed, if it is a condensed matter-like model, it will not be for sure something that we realize in the lab if you recover Einstein field equation. But if you would have a system that with the same, procedure of analog gravity recovers Einstein field equation and the standard model, you don't need it to just, you need to recover all the standard model of particle physics. Then I would say that the problem would still lie in the fact that these are systems that by construction they live in a container space-time, a flat space-time. And so there the question would be, what is this container space-time? So still it would be, if it's not a container space-time, but is, a variety, a manifold that somehow is not a space-time, but in which these atoms of space-time work, then in a certain sense it's no more an analog model, then it's really a quantum gravity theory. So for me, the crucial point is that the analog gravity model cannot be totally background independent, which we know is a crucial theory,
but that's where I have ideas. That's exactly where I have ideas. But okay, so you're basically, let me. We will discuss this in private with more time. But so the point is just that you can have a map of equations, but with that should come an understanding of what is this background structure that, however you interpret it, is there in the analogs in the condensed matter system. the flat background, the flat space-time of the lab, even if you manage to recast the dynamical equations of the fluid in some generativistic form, but when doing that, somehow you have to explain away what is going on with this flat space-time background on which you started defining your fluid. So you have to.
But I think you cannot exactly, and I don't see really. I mean, it is a very hard problem, not to even in a sense is how you can recover general relativity without doing that. The two things must happen at the same time. No, you need to get rid of this background structure.
I have ideas.
Yeah. Okay.
Yeah, I know you're worried when
I'm worried.
Look. Okay, but I don't want to start discussing these further crazy ideas in public. Let me introduce a last topic, because we've been talking for a long while already. But we mentioned quantum gravity at several points, but you also mentioned somehow, strangely enough, in the same context, observations, and the fact that these regular black holes or ultra compact objects motivated by quantum gravity could have observable consequences. You mentioned that all these emergent scenarios could have observable consequences, and then we even discussed that there could be at least some features of quantum gravity reproduced in a lab, not even in astrophysics, in some fluid system. And it's clear that you mean it, because you actually worked. You were given money to work on. You were actually
amazing.
paid. It's amazing. You were actually paid to work on quantum gravity phenomenology. Now, people who listen, I mean, the very idea that there is something like quantum gravity phenomenology comes as a surprise, because if there's one thing that people thought of knowing about quantum gravity was that, okay, it's a future theory that we have to develop, very fancy, but also very mysterious. But it deals with such high energies and small scales and distant scales and so on, that okay, maybe we will have it in theory as in mathematical equations, but we will never be able to test it. So what is all this quantum gravity phenomenology business?
The quantum gravity phenomenology is a big label that identify many approaches, but let me try to give you the gist.
Let me just I interrupt you just for a second, but it's for people who are listening. So quantum gravity people who try to find the theory of quantum gravity with the equations are, as we said, very brave. But then there are even people that have been working on quantum gravity phenomenology. So that even
quantum gravity is really relaxed.
It's like assuming that they find the theory of quantum gravity, we already go ahead and tell them what the predictions should be and what the constraints are from observations. I don't know who is braver here.
Well, but if you think one of the challenges that quantum gravity has always faced is that we don't have observation at the Planck scale, at the scale where quantum gravitational effects should be.
So that's it.
So the gist of quantum gravity phenomenology is not devising experiment that can prove the Planck scale. The gist is different. It's the following. It's that, okay, we don't know quantum gravity and we don't know what happens to the Planck scale. But whatever it happens, it could lead to a finite possibility of new physics of deviation, relic, basically, physics of what is happening at the Planck scale that should be visible at energy which are below the Planck energy. So, for example, imagine that the space-time is discrete in the way in analog gravity it is. In analog gravity, generically you have that this collective excitation have a dispersion relation. That means a relation between energy and the momentum of the particles of these effective fields moving on this effective space-time, which is the relativistic one. Basically, energy is proportional to the momentum, only at low energy. At high energy, when the energy are large, but not necessarily the energy at which the spacetime is discrete. Before that, you see deviation from the standard behavior. For example, that means that the velocity can be larger than the speed of sound at very large energy. Now, this is basically in jargon called effective Lorentz breaking. Means that one of the crucial tenets of crucial symmetries that we built in our theories of matter would be basically violated by high energy, but energy below the Planck scale. This would be a remnant of the discreteness. It's not the discreteness itself. You don't need the detail of the discreteness to know that the collective excitation generically has this modified dispersion relation. Now you can ask yourself, okay, let's assume that, I don't know, photons and electrons, elementary particles that we are very familiar with, have this kind of behavior, modified dispersion relation, and that at the Planck scale, they would have these effects. I mean, they would be suppressed at the Planck scale. You would say, okay, forget about it. I mean, you need to reach Planck energy again to see these effects. But then here comes the subtlety. Especially in astrophysics, you may have a tiny effect, tiny, ultra tiny effect, accumulating over cosmological times, which are a very long time. So even if you take something much smaller than one, you multiply by a number which is huge, humongous, then you get something that might be order one, and then it's visible. Another thing is when you have a reaction between elementary particles, the scale that matters, for example, to be able to produce some kind of, from two photons getting an electron and a positron, the mass scale that is read, the energy scale that is read, is set by the mass scale of the electron. So it's that scale that should be comparable to the tiny the ratio between the energy of the particle and the Planck scale. So you may have effects which are visible, especially in high energy astrophysics, because there you have really very high energies, even in our universe without reaching the Planck energies. And then you can start to say, okay, let's look at that object in the sky. You have, that, for example, the Crab Nebula. The Crab Nebula emits synchrotron radiation. You know how the emission works, how it would be affected by this modification. And you see that even this tiny modification could dramatically affect for example, the synchrotron radiation from the Crab Nebula. Then you have a window of opportunity where you can test a constraint on some new physics at the Planck scale by looking at energy well below the Planck scale.
So, in fact, if I remember correctly, the one possibility of such Lorentz breaking is already ruled out exactly by observations of the Crab Nebula radiation.
Exactly. Basically, already using an object like the Crab Nebula, you can cast a constraint on the lowest order. There are different powers with which you can introduce the Lorentz breaking. If it is suppressed just by one power of the mass of the Planck mass, then you can already severely constrain. Without is a big word in physics, but definitely you can say that is very constrained. That means that is very difficult that is there. Basically, I agree with you that it's basically ruled out correction which are suppressed only by one power of the Planck mass. But if you go up suppression which are suppressed by two powers of the Planck mass, that for other reason are favored theoretically because they are basically what you would predict if you expect that the discrete symmetry of nature, what is called charge parity and time reversal symmetry, are the combination of these three is preserved in quantum gravity. If it is preserved in quantum gravity, you expect other kind of higher order terms to be there and not the lowest order that have already been constrained. And these higher orders that are weaker constrained due to the fact that we don't understand so very well the physics of the ultra energy cosmic rays.
But so the message. So the general message is that we cannot hide ourselves as quantum gravity theorists behind the Planck scale. I mean that.
If your theory of quantum gravity predicts Lorentz violation with the order 1 over m, that are basically suppressed only by one power of the Planck mass in the energy scales, then you are in trouble. Your theory of quantum gravity is basically ruled out.
It's even worse than that as a quantum gravity theorist, because it means that we cannot even work, safely in the warmth of our offices, taking our time and putting forward speculations over speculation, because this stuff can be tested in principle. And in fact, we somehow it's really our fault as quantum gravity theorists that we didn't come up with enough precise enough predictions for these possible effects, because otherwise the technology could in principle be already there to check our theories, to constrain and test our theories.
Let me tell you the another things that you see, quantum gravity phenomenology is also a theoretical value, not just an experimental or observational one, because if you think about the possible deviation below the energy scale of the Planck scale, below the quantum gravity scale, that can be left over by the quantum gravitational behavior, you find out again that there isn't this huge sea of possibility. For example, if you have intrinsic discreteness, like most quantum gravity models have, it's very difficult to reconcile this discreteness with Lorentz invariance, with the special relativity. It is possible, but if you don't want to have a breakdown of Lorentz invariant, then it's somehow where you put this scale, this fundamental discrete. You can put it, of course, in the fact that you may have that operators, also the angular momentum in quantum mechanics is quantized. But at the end of the day, when you go to the limit in which you want to describe the emergent spacetime from your structure, if you have the scale floating around, for example, if you don't have Lorentz breaking, generically you get a non-locality. You get that your theory has non-local terms, and these non-local terms are providing another set of possible tests. For example, non-local effective field theory is a very interesting branch of research for quantum gravity phenomenology, and there maybe is not going at high energy like in high energy astrophysics. You need more precision. You need more laboratory tests. And then there is another branch of observation, but again, it's not completely a free meal. It's not that you can say, my theory is non-local, I don't care. Non-locality can be tested.
So this is another example of what I had in mind. I mean, quantum gravity theorists can write down and speculate about different models, but then we are already constrained by observations or by possible observations in what we are allowed to speculate freely with, and what instead it's really a challenge. I mean, we should be very careful that discreteness, as you said, or non-locality have consequences, and these consequences are not forever hidden at high energies or small distances. So they, in principle, can percolate to observable effects.
And yes, exactly. And we are getting better and better with experiments, even in lab experiments, at probing this kind of tiny deviations. And I think that from this point of view, this could provide a very important guide for people doing quantum gravity, because finally you will have some kind of boundary imposed by nature, and not just by the self-consistency of the mathematical theory.
I see. Okay.
No, we cannot exclude that there are very good theories which are self-consistent, but nonetheless they do not describe the reality, right?
I wouldn't be surprised at all. And let me conclude. Well, let me conclude with putting you in the spotlight, because I don't see why we should only bash quantum gravity theorists. Okay, you convinced me that you are shaking the foundations, because a number of things you mentioned are clearly foundational, and they challenge some very basic assumption of our physical theories and physical understanding of the world. And you convinced me that some radical revision is needed. I mean, I didn't need to be convinced, but I hope that also people who are listening are now convinced. I do my fair share of speculative work in the office. They again, believe it or not, they still pay me for that, but for a while at least. But I want you to speculate. So, if you have to guess, what is the idea that we take for granted in doing physics, and will probably have to go?
This is a very good question, but a very dark one. One thing that is bothering me, and I think that it's basically very rarely questioned, is quantum mechanics. I mean, in Germany, in quantum gravity, we try to quantize gravity, but we don't really take into account that quantum mechanics, as we know it, can also be emergent. Because there is people that have speculated about this, very good people. But somehow the core of the work nowadays in quantum gravity start taking as as axioms the basic tenets of quantum mechanics. It is possible that in order to conjugate gravity in quantum mechanics, you don't have just to quantize gravity. You have somehow to mold the two together, but not just shaping one to adapt to the other, but you have to mold them together by shaping both of them, reshaping both of them. It may be that quantum mechanics as we know it is some kind of low energy limit of a more general theory. And this more general theory would be the one that goes together with the quantization of gravity.
Somehow, we hinted at that already when we were mentioning the information paradox, because that's a paradox, assuming that quantum mechanics has to work as it normally does with information preserving dynamics, and that's one.
Yeah, no, there you see there is an argument, Daniele. There is an argument because people will tell you, okay, but given that the paradox start to be present already when you have evaporated half of the entropy of the black hole, in instance where the black hole is still macroscopic, it looks like you're not sufficiently far, you're not in a terra so incognita. Well,
but that's exactly what the quantum gravity phenomenology has told us about, that there could be effects of quantum gravity or radius scales which are not the
could be
ultra microscopic there. So I see the argument.
Evaporation effects. There could be that there are tiny deviation from the standard history, even when the black hole is very large and starts to evaporate. But what is happening is that they are ultra tiny, and then, however, accumulating over all the lifetime of the black hole, then they become very relevant in this story. The problem is that if you think of the information loss paradox, only Hawking at the start tried to modify quantum mechanics with the so-called superscattering matrix and so on. But then it basically didn't work, because as you fiddle with quantum mechanics, immediately you get in trouble. It's very difficult to modify quantum mechanics without getting something going wrong. And so basically, since that point, most of the people have tried to modify the gravitational side of the story to reconcile.
That's also what you mentioned at the beginning. I mean, you try to modify gravity by, for example, curing the singularity and but then you have to worry that things become quickly unstable. Or, you want to say, okay, it's not really a black hole, it's just an ultra compact object. Okay, but it's not easy to modify GR to accommodate that and the rest of physics. So let me just conclude, because we discussed for very long already. We should be up for surprises, whether they come from modified gravitational physics or modified quantum mechanics, or some new observed effect that we were not expecting and coming from quantum gravity, or revealing the thermodynamic properties of space-time. Surprising are exactly what we should expect, which is not easy.
Yeah. And we should look at this problem, I think, a bit thinking out of the box, because it's clear that we've been thinking into this problem for too many years now. And in a sense, they require probably a resolution which is out of the box. That I'm pretty convinced. Otherwise, we would have found it. Very brilliant people has worked on this problem so far. And no, I was not.
Well, okay, not only brilliant people.
Okay. So anyway, I think that definitely these ideas may help us at least thinking in a different way to this problem. Maybe they do not work. Maybe they do put you on the right path. but I do think that they are part of the way of thinking in a normal way, quantum gravitational problems and the nature of space-time. And if they may give at the end also some constraint, even just telling you this cannot be, then at least excluding some roots, it's more information that we have now.
Very good. Okay, well, what else? Thank you, Stefano.
Thank you, Daniele. Bye-bye.
Ciao.